Now, when a problem has more than one condition which needs to be solved, then we're going to be dealing with a system. Okay, so remember that word there, system? That means that we're going to be dealing with more than one. Okay, so it's going to have a system of equations or inequalities is going to be needed, and the point where the lines meet or shaded regions where they're both located is going to be our answer. And when we get into our next section on optimization problems, we're going to be dealing with systems of inequalities and sometimes coming up with systems of inequalities as well. In your assignment as well, you're going to have where you have a few systems and you have to try to find multiple problems. So there's going to be multiple problems that need to be solved or multiple solutions that need to be found. And so we're going to need multiple either equations or inequalities to solve that. But we're going to be dealing with the exact same variables, and so the variable thing is going to stay exactly the same. All right, so let's look at number 6 here. We have a shipping container that contains large and small tires. A large tire weighs 60 pounds and a small tire weighs 20 pounds. Now the container has a total of 250 tires, which have a total weight of 7,000 pounds. We have two solutions here. We know the number of tires and we know the total weight of the tires, but we do not know how many large and how many small tires we have. And so the number of large tires and the number of small tires, okay, that are on this shipping container are our two variables, the two things that we don't know. Okay, domain and range. Again, we always come up with domain and range, and D and R are just fine if you want to write it like that. Domain is going to be the solution set for our x's, or number of large tires. We cannot have negatives, we cannot have decimals. So x has to be a part of all real, not all real numbers, sorry. X has to be a part of our whole number system. That was a mistake there. All right, x has to be a part of our whole number system, and y in the same way has to also be a part of our whole number system, because we cannot have part of a tire and we cannot have a negative number of tires. So two things that we need to come up with. All right, first one, total number of tires. Okay, so number of small tires plus number of large tires is going to equal our total number of tires. So x plus y is equal to 250. Wasn't too hard, was it? All right, so if we add the two together, we get a total of 250. That's our first one there. That's our first problem, and we have a solution for that right there. Our second one is that the total weight has to be 7,000 pounds. Now again, we're still dealing with number of tires, so it's going to be the total weight of large tires and the total weight of small tires. Well, to find the total weight of our large tires, we have to multiply by 60. So we're going to have to take 60 multiplied by x, and then our small tires are 20, so 20 multiplied by y is going to equal to our total of 7,000. This is our second solution to a problem that we have. These are two separate things, and now both of these are going to have to be solved. Okay, and we have to figure out now what pair of x and y, how many large tires and how many small tires do we need to satisfy this solution set here. Okay. Now again, we could type this into Desmos and it would shoot up our number or our point, and we could find a solution set to these if we'd wanted to. Okay, but in this case here, because we know an exact number, okay, we have a total of and a total of, it's exact, we're going to have one solution set or one solution to that. Number 7 is a little bit different. Okay, number 7 is going to be an inequality because there are a couple different solution or cases where we have limitations. Okay, so because of the supply of parts is limited, a toy manufacturing company can make no more than 40 racing cars and 60 SUVs each day. However, the company can make a total of 70 or more vehicles per day. So it can make 70 or more, but it can make no more than 40 racing cars and no more than 60 SUVs per day. Well, we don't know how many of each we're going to make. Okay, so those are going to be our variables. So x is going to equal the number of racing cars made, and y is going to be the number of SUVs made each day. Now again, throw some restrictions in there, or at least our domain and range. Okay, domain and range. Okay. Again, these are going to be whole numbers because we can't have negatives and we can't have decimals. We're not going to make part of a car or part of an SUV. So we're going to have whole numbers right there. All right. Now, in this case, we actually have more than two different problems, so to speak, that we're trying to solve. We're told that we can make no more than 40 racing cars, meaning that X has to be less than or equal to 40, okay? No more than 40 racing cars. We can make up to, but not over. So X has to be less than or equal to 40. That's our maximum there. Okay, so that's one of our solutions there. And we're also told that we have to have less than or equal to 60 SUVs. Okay, those are two very simple and they're straightforward. They're just, the value has to be less than a certain amount. Okay, we don't even need both variables in there, so we could have something that looks like that. Now the company can make a total of 70 or more vehicles per day, so this is now where we're combining the two. And so we know that X plus Y is going to be greater than or equal to 70. Because we know that when we combine them, it's going to be greater than or equal to 70. Okay, so we're making it bigger. And so now in this case here, we have 3 inequalities, and we have to find the region that is made up by these 3 inequalities. And that would be our solution set to this problem.